The next thing which we are going to look at is measures of dispersion. So why do we need to know about measures of dispersion? So measures of central tendency actually captures what we call the center or the typicalness of the data set. So what does measure of dispersion capture? Why? First of all, even before going to define what is a measure of dispersion, let's understand why do we need a measure of dispersion. Towards this, let's look at two data sets. The first data set is both the data sets have 5 observations each. The first data set has observations 3, 3, 3, 3 and 3. The second data set has observations 1, 2, 3, 4, 5. Let's work out the measures of central tendency for this data set. So if we work out the measures of central tendency for this data set, we observe the following. The mean of the first data set is 3. The mean of the second data set is also 3. Because the mean of the first data set is 3 plus 3 plus 3 plus 3 plus 3, which is 15 divided by 5, which is 3. The second data set is 1 plus 2 plus 3 plus 4 plus 5, which is again another 15 divided by 5, which is equal to 3. We look at the median. The number of observations is odd, which is 5. So 5 plus 1 is 6. 6 by 2, the third observation. The third observation in data set 1 is 3. Again, the median for the second observation also is 3. The mode for the first data set 3 appears, there is only one value and 3 which appears 5 times. So the mode is 3, whereas for the second data set there is no mode. However, when you look at this data set and only if the numerical summaries and the measures of central tendency are given to you, you somehow tend to believe that both the data sets are very similar in nature because the mean and the median of both these data sets are the same. However, we see that both these data sets are very different from each other. So when they are different, we want to see that is there any other measure that can capture this difference, and hence we need to understand what is a measure of spread or dispersion. The first understanding we need to have is I have to describe this difference quantitatively, which will actually tell me what is the amount of variation, what is the amount of spread of a data set. So the descriptive measures are popularly referred to as measures of dispersion or measures of variance or measures of spread. What are the key measures of variation we are going to understand or dispersion we are going to understand in this course? We start with defining what is a range, then we go on to define what is variance. Once we establish what is a variance, variance is the most frequently used measure of dispersion. We define what is a standard deviation, and then after introducing what are percentiles, we'll introduce the notion of an interquartile range. So let's go ahead and understand what is a range. A range is defined, range of a data set is defined as the difference between its largest and smallest value. So the range, as the name suggests, is the difference between the largest and the smallest value. So the range is basically maximum minus minimum, where maximum is the largest and minimum is the smallest value. So let's go back to the two data sets we have. The first data set was 3, 3, 3, 3, 3. The second data set was 1, 2, 3, 4, 5. The maximum of the first data set is 3 because I have only one data value in that. The maximum of the second data set is 5. The minimum of the first data set is again 3. The minimum of the second data set is 1. Hence, the range of my first data set is 0, whereas the range of my second data set is 4. So you can see that the range in a sense tells us more about the data sets than what the measures of central tendency actually revealed. But however, what is the problem with the range? Now again consider the two data sets. The first data set is just 1, 2, 3, 4, 5 and the second data set is 1, 2, 3, 4 and 15. These two data sets differ with each other only in one observation, namely I have a 5 here whereas I have a 15 here. So this is the key thing where they are different. So the maximum of the first data set is a 5, the maximum of the second data set is a 15, the minimum for both the data sets is 1. So the range of the first data set is 5 minus 1, which is a 4, whereas the range of the second data set is 14. So as you can see, very similar to what we observed when we discussed about the mean, we see that the range is extremely sensitive to outliers. So the range is an extremely sensitive measure because the range takes into consideration only the extreme values to compute it, the formula. Now the next measure of dispersion which we are going to talk about, and this is the most frequently used measure of dispersion, is what we refer to as the variance of a data set. In contrast to the range, the variance takes into account all the observations. What do we mean by this? Again, the range takes into account only the minimum and the maximum, namely the extreme observations are taken into consideration when you actually compute the range, whereas the variance takes into account all the observations. So the one way of measuring the variability is to consider the deviations of the data value from a central value. What do we mean by this? Suppose I have my data x1, x2, x3 up to xn. I have a measure of central tendency. For now, let me call that x bar. I have this measure of central tendency which I have defined. So I have a measure of central tendency which I have defined as x bar. Okay. So the deviation of the data values from this central value is x1 minus x bar, x2 minus x bar, and so forth, xn minus x bar. This is what I mean by the deviation or the difference of each of the data points from its central value. And the central value I have chosen here is the mean. Okay. Now, one thing is, in a given data set, for example, let's again take a 1, 2, 3, 4, 5. I know x bar for this data set is 3. The deviation of 1 from 3 is a minus 2, 2 from 3 is minus 1, 3 from itself is 0, 4 from 3 is a plus 1, and 5 from 3 is 2. We can see that these are the deviations of the data set. But then afterwards I need an aggregate measure. I just cannot give the deviation. One possibility is, okay, if I sum up all the deviations, I see it goes to 0. Hence again I see that summing up the deviations is not a very good measure of the variability, even though I have taken all the data points into consideration. So what variance, the population variance and the sample variance does is the following. It looks at the deviation of each of my data set from data point from the central value and it squares it up. It adds the squares of the deviation. So sum of squared deviations from the central value and it averages it. Again I repeat, it takes the deviation of every data point from its central value, it squares the deviation and adds up all the deviations and divides it by a number. Now, if we are talking about a population variance, then the variance of a population variance or the population variance given by sigma square remember population mean is mu. So I have x1, I have x2, I have xn, which are my population units. X1 minus mu is the deviation of the first unit from the mean. X2 minus mu is the deviation of the second unit from the mean. Xn minus mu is the deviation of the nth unit from the mean. I square each of these deviations, I add them up, I get the numerator. If I divide the total sum of square deviations by the total number of observations, I refer it to the population variance. However, when I talk about the sample variance, again I have x1, x2, xn, n is my sample size, the mean is given by x bar. I look at the deviations of each data point from the mean and I square it up, the sum of the square deviations divided by n minus 1. Notice the difference between the population variance and the sample variances. The population variance, I divide the sum of square deviations by the total number of observations. When I refer to the sample variance, I divide the total number of sample square deviations by the number of total observations minus 1. There's a reason to do so. The explanation is out of the scope of this particular course, and you learn about this as you go forward. The notation for a population variance I refer as sigma square, sample variance I refer as S square. Okay. So I repeat, the numerator, be it the population variance or the sample variance, is the sum of square deviations of a data point from its mean value. So the numerator is the sum of square deviation. The denominator for population variance is n, whereas it is n minus 1. The reason will become very clear in the forthcoming courses. But for now, we are going to restrict ourselves to sample variance. So again, go back to looking at the same example, that is the marks obtained by the 10 students in an exam. So the mean was, remember, we computed the mean to be 59. So let's compute the deviations. So you can see that the deviation is given here. 68 minus 59 is 9. 79 minus 59 is 20. 38 minus 59 is minus 21. Okay. And the square deviations here, I have a 81. I have a 400. So forth, I keep writing this and I can see that I can find out what are the sum of the square deviations for each one of the data set. So this is 68 minus 59. This is 79 minus 59. This is 38 minus 59. 68 minus 59. 35 minus 59. So you can see that, and this is 66 minus 59. This is 7 square, 1 square, 11 square, 24 square. The sum of the square deviation minus 24 square, minus 1 square, minus 7 square. So the sum of, so the numerator xi minus x bar whole square is 1898. I have n equal to 10. To compute the sample variance, I divided by 10 minus 1, which is 9. And you can see that my population variance is 189.8, whereas my sample variance is 210.88. Okay. So now let's look at how to compute this using our Google Sheet. So in our Google Sheets, this is again my data is what I have highlighted here. Okay. So now if you look at this portion here, this is the squared deviation. So you can see that this square deviation is B2. B2 is my data point. B13 is my mean whole square. So this corresponds to the 81 I have here. Okay. Similarly, I have a 400, the second data point. I have 441, the third, and so forth. My total sum of square deviations as highlighted here is 1898. So this divided by my 10 would be 189.8, but when I am dividing it by 9, I get 210.88. Now the same thing, if you use the function var.s, s to represent the sample statistic, var.s of the array returns the sample variance. I repeat, var.s returns the sample variance, and we can see that this is equal to the sum of the square deviation divided by 9, and I get the same value. Okay. Now the population variance is nothing but, now as in the earlier case, let's see what happens to the variance when we manipulate the data set. What we mean by this is, what would happen to the data set if I add a constant or I multiply each one of the values with the constant. So what would happen if I add a constant? So I have yi is xi plus c, where c is a constant. So again, let me just look at three numbers, y1, y2, y3. I have x1, x2, x3. X bar is the mean of these three numbers. Y bar is the mean of these three numbers. We have already seen y bar is c plus x bar. This is already what we have seen. So now when I compute my variance for the new data set, I get a yi minus y bar whole square summation. This is my numerator over I going from 1 to n. My yi, so it's xi plus c, that is each yi. Y bar is x bar plus c. So you can see that this is xi plus c minus x bar minus c, which is same as xi minus x bar. Is that clear? So I have yi minus y bar is xi plus c, because each yi is xi plus c. Y bar is x bar plus c. So it is xi plus c minus x bar minus c, which is these two get cancelled out and I get xi minus x bar. So I have the numerator, which is yi minus y bar whole square, to be the same as xi minus x bar whole square, summing up over all values of n. Hence, variance of y, which is 1 by n minus 1, the number of observations is same, yi minus y bar whole square, I going from 1 to n, is same as 1 by n minus 1, summation I going from 1 to n, xi minus x bar whole square. This we already know is the sample variance of x. Hence, if I add a constant to every value of my data set, the variance of the data set does not change. The new variance is equal to the old variance, and that's what we have just seen. So let's look at an example to see what is happening. Recall, we just computed the marks of the students and the sample variance is 210.88. We add 5 marks. The new data set is this, and you can see that The new variance of this data set is also 210.88. In general, we have adding a constant does not change the variability of a data set. Let's go back to this example. Again, this is my original data, the one that is highlighted. The variance was 210.88. I add a constant and I get this as my data set. You can see that the variance for both these data sets is the same. So, adding a constant does not change variability of a data set. What happens when we multiply the data set with a constant? Again, I have my y1, which is x1 into a constant, y2, x2 into a constant, yn, which is xn into a constant. I know y bar is x bar times the constant. So, my yi minus y bar is going to be xi constant minus xi x bar constant. Sorry, this is x bar constant, x bar constant. I can get the constant outside, so I can write this as constant times xi minus x bar. Okay, I repeat, for every yi minus y bar is same as c times xi minus x bar. So, square is going to be c square times xi minus x bar. So, summation I going from 1 to n yi minus y bar whole square is going to be c square summation I going from 1 to n xi minus x bar whole square. 1 by n times minus 1 is going to be n minus 1. Hence, variance of y is nothing but c square variance of x. Is that clear? So, this is my data set. I already know y bar is x bar into c. I just substitute the values and I get the variance of y is c square variance of x. So, we have the following, that if yi is xi times c, the new variance is c square times the old variance. We have just established that relation. We can verify that using our data set. I already know the data variance for the data set is 210.88. I multiply it with 0.4. I know this is my data set. The mean of this new data set is 23.6, and I can compute that the variance, which is 33.74, is 0.4 square to 10.88. So, you can see that when I multiply with a constant, I get 33.74 is my variance, and I can verify that this is 0.4 times the old variance. So, this 0.4 times the old variance is my new variance. So, this is how we compute the data set with adding a constant and multiplying with a constant. Another useful measure of dispersion is the standard deviation. The standard deviation is nothing but the square root of the variance. Now, why are we interested in the standard deviation? The standard deviation is referred to by the small lowercase letter s. So, the standard deviation is the square root of the sample variance. Similarly, I can define this population standard deviation also. So, why do I require a standard deviation? Remember, whenever I talk about a numerical measure, there are units associated with the numerical measures. For example, if I were looking at ages of people, or I was looking at heights of students, or I was looking at the weights of students, 68, suppose 75, instead of marks they were weights of students measured in kilograms, then the average, which was 59, which I did not given any units, if it were weights would have been 59 kilograms. In other words, the average of a data set has units which is same as the original measurement. I repeat, the average of a data set have the same units as that of the original data set. But when I am computing the variance, what I do is I take the data set. So average has the same units as the data set. So if it is kilogram, this is a kilogram, this is a kilogram. I am squaring it up, so difference will also be kilogram. So the square is not going to be kilogram, it would be kilogram square. I add units of kilogram square. So my units of the variance is square of the units of the original variable. Okay. So to overcome this, what we do is we define what is called the standard deviation, so that the units of measurement of this standard deviation and the original units of measurement are the same. So if I am looking at variance, I have a unit which is kilogram square. I bring it back to kilograms. So the sample standard deviation is measured in the same units as the original data. If the data is in kilograms, the units are also in kilograms. So what happens when we add a constant to the data? So again I have x1, x2, xn. I am adding y, I am getting y1, y2, yn, where each yi is xi plus c. I know variance of yi is same as variance of xi. Hence, square root of variance of yi, the positive square root, is the same as the positive square root of variance of xi, and hence the standard deviation is also the same. The new variance is equal to old variance. Recall this. The sample variance were the same. The sample standard deviation is also the same. Hence, the constant does not change the variability. Both new variance is equal to old variance. New standard deviation is equal to old standard deviation. In other words, adding a constant does not change the variability of a data set. What happens when we multiply a constant? Again, you know that if yi equal to c times xi, we saw the variance of y is c square times variance of x. Hence, the standard deviation of y, which is the square root of variance of y, would be square root of c square variance of x, which is c times root of variance of x, which is c times standard deviation of x. So when I multiply with a constant, I know new variance is c square variance, old variance. So when I look at the data set, you can see that the standard deviation is 0.4 times 14.32. So new standard deviation is c times old standard deviation. Okay, this is my c, and I can see that that is the c times the old standard deviation, which is 14.522. So let's look at this in our, so you can see that when I multiply it with a constant, the standard deviation of my original data set is 14.522. This you can verify is nothing but my square root of the sample variance. So, square root of the sample variance is 14.522. In the Google Sheets, the command is STDEV, standard deviation of B2 to B11 gives the standard deviation. I can see that when I add a constant, the standard deviation remains the same. You can see that the standard deviation for these two, the highlighted columns, are the same. Whereas when I multiply it with a constant, you can see that the standard deviation is 5.808. You can verify this is 0.4 times my standard deviation is 5.808, and you can see that is equal to my standard deviation of multiplying with the constant. Hence, when we multiply it with a constant, you can see that the standard deviation, the new standard deviation is the constant times your old standard deviation. Okay. So, adding a constant does not change the variability of a set. Multiplying with a constant changes the variability of a set by a scalar multiple. So, what we have seen so far is, we started with range. We saw the range is very sensitive to outliers. We defined what was population variance and sample variance. The definitions are very important, because just by talking about variance, we need to know whether we are referring to population or sample variance. The numerator captures the sum of squared deviations. The denominator is the number of observations if you are considering population variance, and number of observations minus 1 if you are considering the sample variance. Then we introduce the notion of a standard deviation, which has the same units as the original data. We also saw that when you add a constant, variability of a data set does not change, whereas when you multiply with a constant, the variability changes.